Our next application of rationalizability, Chapter 8, is the social unrest game. In the social unrest game, we consider circumstances in which why it seems that in some instances a phenomena very quickly fizzles out without really catching on, and sometimes it goes viral and everyone catches on. You could post a video on TikTok and you might only get 20 views in that very same video. If things were ever so slightly different, you might get 1,000,000 views, and so it's one of those things where it seems like for very tiny, almost imperceptible reasons, you can have something either completely fizzle out or go viral based on something. It's hard to pinpoint what it was that made that determination. One of those applications would be social unrest, or when you get revolutionary conditions in a country, like something like the Arab Spring. Why is it the case that we get people who can, a few people out in the streets can, in some cases can turn into millions very quickly. In other cases, it completely fizzles out. So we're going to create a model that addresses circumstances like this, a very simple model, and we're going to use rationalizability to solve what's going to happen in the model. So suppose there's a continuum of players. By continuum, I mean there's essentially it's equivalent to assuming there's an infinite number of people, which when you studied introductory micro, it's also what you assumed there, because you assumed that quantities were infinitely divisible. It's the same assumption that we used in introductory micro. It's why you had a nice smooth linear demand curve instead of a staircase demand curve. That was implicitly the assumption of a continuum of players, or a continuum of available goods in demand. So we're going to suppose there is a continuum of players, and we're going to index those players I from 0 to 1. So in the 0-1 interval. So that means that players are uniformly distributed on the 0-1 interval. So player 0 represents one particular person. When I equals 0.3, that's another particular person. When I equals 0.654, that's another particular person. Person 1 divided by pi is another person. So there's an infinity of people, each of them located on a distinct point on the 0-1 interval, and we're going to denote the index of each player by I. So if I refer to I equals 0.7, that's person number 0.7 located on that interval. Each person has two choices. They can protest or stay at home, designated as H. Okay? The utility for each person I is denoted as following. If they stay at home, before we get to that, let's let X be the fraction of people who end up protesting. So X is the fraction of protesters. Okay? And so the utility of person I, should she stay home, which is a function of both her choice and the fraction of people who protest. So the utility is going to be impacted by how many people are on the street. If she stays home, her utility is 4x minus 2. All right? So she clearly, every person I would benefit from more people protesting. So this is an environment in which everyone would like the government to be overthrown, or some policy to be changed, or something of that nature, right? So all their interests are aligned. When they stay home, their utility is not affected by who they are. So they all receive identical utility if they stay home. All right? It just depends on how many people actually stay home. Those who do stay home will all get the same utility. However, If they protest, their utility is going to be depending on where they're located within that continuum. Okay? So they're going to get twice the utility that they would get by staying home. Now notice that could be either good or bad, right? So if everyone protests, so x is equal to 1, then if they stay home, their utility would be 2, and if they protest, their utility is 4, right? So it's like it doubles their happiness if they're out on the street protesting relative to if they stay home. So you're better off protesting because you were part of the movement, right? You feel good about that. But if x is small, like close to 0 or equal to, say it's equal to 0, so very few protesters out there, then if you stay home, your utility is -2, but if you're on the streets, your utility is -4, right? So it's like that's the situation where if you're the only one that goes out there, everyone else stays home, you're going to get arrested and you're going to be in a world of problems. So other than just being disappointed the government was not overthrown, you face some extra circumstances that are negative, okay? But in addition to that dynamic, we have another term, which is plus alpha times I. Here again, alpha is a parameter. So it's a constant parameter. Right? So everyone in this particular society knows exactly what alpha is. It's some number bigger than 0. In one economy, one society, it might be 1. In another society, it might be 5. In another one, it might be 3.2. Right? So alpha is a parameter. Clearly, the larger alpha is, the more utility people get from protesting. So the utility of protesting is increasing in alpha. In addition, your location along the index indicates how much you would like the government to be gone, right? So if your person number I equals 1, you have you're going to add the whole entire alpha to your utility if you go out and protest, or you really, really want the government gone. Person number 0 doesn't get any boost from alpha at all. Person number 1/2 gets half the boost that person number 1 does, etc. So the more your location matters. So basically we have a society where we have an infinite number of people. They're indexed by this I, and the higher I is, the more they dislike the government. So everyone's just a little bit different from everyone else. Okay? And that's our basic model. And so now we're going to think about dominance for the individual level, so rationality at the individual level, and then we're going to think about rationalizability, iterative dominance. All right? So this is our basic model. And so what we're next going to think about are the sets of dominated strategies. And yeah, so let's do that. So when is home dominated for I equals 1? So when is it a dominated strategy for person number 1 to stay home? Right? We want to find the condition under which this person, regardless of their beliefs about the fraction of protesters out there, so regardless of who they think is out there protesting, this person wants to protest no matter what, right? So even if they're the only person in the entire protest, they're that one person standing, they're tank man, right? They're just standing out in the street by themselves, they're going to go anyway, okay? It doesn't matter what anyone else does, they're going to be the one protesting, okay? Why person number 1? Why are we interested in that? Well, person number 1 is the person who most dislikes the government. And so we want to know what are the conditions in which that person is going to protest no matter what. Because if person number 1, if whether or not they protest depends on what their beliefs is, right? So we know that everyone protests if everyone thinks the number of protesters is big enough, right? Because if X is really big, everyone gets better utility by protesting than not protesting. So we know there's some conditions, some beliefs for which everyone would want to go out and protest, right? But what we're looking for is, even under the most pessimistic beliefs, when would person number 1 be willing to go out and protest anyway? So even if they think X is equal to 0, they protest. Why person number 1? Well, if that person goes and protests no matter what, and a couple other people do as well, like people just to the left of number one, then no one is allowed to believe that no one protests, right? So if we have a group of people who go out in the street and protest, even if no one is protesting, well, then you can no longer have a belief that no one protests. So your beliefs have to be that at least some people are on the street. And if your belief is that some people are on the street, then even more people protest than when no one protests. Well, if even more people protest, then the fraction of people you believe are going to protest has to be even bigger, and the whole thing is going to quickly unravel so that the rationalizable action in this society is going to be for everyone to go on the street and protest, right? So this is the idea of the social unrest model. You can get, it's rationalizable for some alphas, for everyone to be in the street, for no one to be in the street, for some people to be in the street, for no one to be in the street, except if alpha is big enough, we're still going to have conditions under which person one goes out anyway, and as long as person number one goes out, it's going to make everyone definitely go out, regardless of what the beliefs are, right? So we're looking for like critical values of alpha, which is going to cause everyone to definitely go out in the street. Otherwise, if alpha is not big enough, you can have many rationalizable outcomes. Okay? So that's the basic idea of what we're going to study here. So when is H dominated by P for person number one? Well, it's when the utility to person one of protesting when X equals 0 is greater than the utility to player one of staying home when X equals 0. All right? So that's what we're looking for, right? So I've translated when is H dominated for I equals 1. I've translated that to math, right? To symbolic notation. Well, it's when the utility to player 1 of protesting, even if X equals 0. Now, of course, if X is even bigger than 0, so if he thinks some positive fraction, well, that's going to make this person like protesting even more, right? So we're looking for the most pessimistic belief under which person one will still protest, because if he protests under the most pessimistic belief, he's going to protest for sure under all beliefs. Okay? So when is it dominated? It's when the utility of protesting is always bigger than the utility of staying home for that particular person. All right? When X equals 0, we have a strict inequality, so it's a greater than, not a greater than or equal to sign. Because it was greater than or equal to, and we had the situation in which equal to, then person number one would be the only person with a dominant, who would consider, who would have a best response to go out and protest no matter what. And person number one doesn't have any weight in this economy. Everyone is what you in introductory micro you thought of as a price taker. They have no impact by themselves. You need a group of people to go, a cluster of people, a mass of people, right? But if the utility of protesting for person one is strictly greater than the utility of protesting of staying home for person one, that also implies it's strictly greater for some of the people just behind number one. So person number 0.9999 may also would find potentially it to be a dominating strategy, and if not, then try person 0.99999, and if not that person, try 0.99999. Eventually, you're going to get a person close enough to one who also protest, and then everyone between that person and one protest, which means you have a positive fraction of protesters, right? That's what we need. That's not a very precise mathematical argument, but it's the intuition for the mathematical argument that we need, and that's good enough for the purposes of our class, all right? So the utility of protesting is equal to 2 times 4 times x, which we've assumed to be 0, minus 2, plus alpha times 1, because we're dealing with person 1, right? And we want to know when is that greater than the utility of staying home when everyone else stays home, which is equal to 4 times the fraction of people who protest, which is 0 minus 2. Okay? So we want to find that condition. So notice that this inequality, we have a bunch of numbers and alpha. So it's going to give us a restriction on alpha. Okay? So we have 2 times 4 times 0, which is 0, negative 4 plus alpha has got to be greater than negative 2, which means alpha greater than 2. Okay? So provided alpha is greater than 2, some positive fraction of people protest. So let's think of a particular example with alpha greater than 2. Namely, let's let alpha equal 3. Right? So the result we showed above, that if alpha is greater than 2, person number 1 will definitely protest, which means some fraction, a positive fraction of people will definitely protest. And the argument I gave you before is that, but that fraction of protesters was willing to protest if no one protests, but now they know by common knowledge of rationality that it won't be the case that no one protests. So there is some protesters, which means even more people will protest, and the process of rationalizability of iterated dominance will take us down to everyone protesting. I want to look through that process with a specific value of alpha that is greater than 2. If alpha is big enough, that process unravels like super fast. Alpha equals 3 is like it's fast but not too fast. So we'll be able to see a couple rounds of iterated dominance before everyone goes out and protests. Okay? So let's look at the case of alpha equals 3 and who has dominated strategy of staying home. Well, the people with dominated strategy of staying home are the people for whom 2 times 4x minus 2 plus alpha times I is greater than 4x minus 2, but again, it's dominated, if that's true, for x equals 0. Okay, so we're thinking, even under the most pessimistic belief, we'll make one minor change here. Remember, alpha, we've already assumed for this particular problem to equal 3. So we're still thinking of a case of dominated strategies. We're still thinking of the case of a fraction of people that, people for whom, even under the most pessimistic belief that x equals 0, who still go out in the street anyway. What we've done, before we were looking at person 1 in particular, and then we solved for alpha. Now we're doing is plugging in a particular value of alpha, and then solving for person number I. So who is the index of the person, of the people who will still go out and protest no matter what. So we're swapping out one variable for the other. So before we popped out person number 1, what are the values of that parameter alpha that make everyone protest? Now we've picked a value of alpha where we know everyone will protest under the rationalizability, and we're looking at the process of that argument for rationalization, right, for iterated dominance. So now we're looking for who is person number I who will protest no matter what when alpha equals 3. Okay? So we get minus 4 plus 3i is greater than negative 2, which means that 3i is greater than 2, so I greater than 2/3. Okay? So, this means that given that we indexed our people from 0 to 1, that person number I equals 2/3, person number I equals 2/3 is indifferent to protesting or not. That person would have the same utility for protesting or staying at home, and everyone above that person, these people, H is dominated. And again, this is for when alpha equals 3. Okay? So, and because person number 2/3 doesn't matter, he's inconsequential in that set, and everyone bigger than him has a mass of x equals 1/3. Right? So that means that 1/3 of the people protest under all beliefs, even the most pessimistic one. Right? Now, you could have everyone protesting right off the bat because they all believe everyone else will protest, right? But in this case, what we're interested in is the people who protest, who protest even under the most pessimistic conditions. That means they have a dominant strategy to protest, right? And H is dominated. Because again, what we're trying to do is show if a fraction of people have a dominated strategy to go on the street, no matter what, then that means that all the other people know that some fraction of the people go on the street, which means even more people definitely go on the street, which increases the fraction of people who definitely go on the street, and so on and so forth. Okay? So, how does the rationalizability work in this circumstance? Well, now it's common knowledge that if alpha equals 3, that 1/3 of the population for sure will protest. It might be more, but it's at least 1/3. So the most pessimistic case is that 1/3 of the people protest. But if that's true, then it's also the case, let me check the utility function real quick, then it's also the case that 2 times, what is that utility again? 4 times x, right? 2 times 4 times x, this time the minimum belief that you're allowed to have in terms of the fraction of protesters is 1/3. Because you know at least 1/3 of the people protest. And that's minus 2. Plus 3, which is alpha, times I, is going to be greater than 4 times 1/3 minus 2, the utility of staying home. Yes. Okay? So again, this is the same inequality we had on the last page, except instead of 0 for the minimum beliefs of possible protesters, we now have 1/3. We all know that at least 1/3 of the people go out in the street. Okay, so because more people were definitely going to be in the street than the expectation that no one's on the street, this is going to make a smaller I than we found before, and a smaller I means even a bigger fraction of protesters. Right? So that's where we're going. Okay, solving this, we have 4/3 times 2, so we have 8/3 minus 4 plus 3i is going to be greater than 4/3 minus 2. Let's see, we have, this is going to be negative, this is going to be 4 is going to be 12/3, so we're going to have negative 4/3 plus 3i is going to be greater than, it's going to be 2 over 3, so 6, so for negative 2/3. Okay, swap the 4 over the other side, we're going to get 3i. It's got to be greater than 4/3 minus 2/3, which is 2/3. So I has got to be greater than 2/9. Looking at our line segment again, 0, 1. Our second round of dominance, so the first round of iterated dominance, is now saying that, look, this person, number I, 2/9, is indifferent between protesting and staying at home, and everyone above I equals 2/9 has a dominant strategy of protesting. Okay? But to derive that, we assumed x was equal to at least 1/3, but now we know x is going to be at least equal to 7/9, right? But now we know the worst case scenario is x equals 7/9 because these people here, all the people from I equals 2/9 who's indifferent, but everyone bigger than this person, there's 7/9 of the population, they all are definitely going to protest. They have an iteratively dominant strategy to protest. It wasn't dominant to protest for all of them. For 1/3 of them, it was, but not for the rest of them. But for the balance of that group, they're going to protest because of iterative dominance. Okay? So now we run one more round of rationalizability. So we know it's going to be, I can't keep my equation straight, 2 times 4 minus, let's see, 2 times 4 times, we know that's going to be at least 7/9, and that's minus 2, plus 3 times I has got to be greater than 4 times 7/9 minus 2. Okay? Again, it's the same as the last two inequalities. It's just in the first case we changed 0 to 1/3, and now we're changing 1/3 to 7/9 because we're increasing the minimum belief of the fraction of protesters. All right, so this is now 2 times 4 is 8, and then 8 times 7 is 56. So we have 56 over 9 minus 2 plus 3 times I is greater than 28 over 9 minus 2. All right, so that's 56 minus 18, which is 38 over 9 plus 3I is greater than 28 minus 18 is 10 over 9. All right, so 2 over 1 is the same as 18. Yes, okay. So that's positive 10 over 9. And so now we're going to get 3I has got to be greater than negative 28 over 9. So I has got to be greater than negative 28 over 27. All right? But this is everyone. Because all I are in the 0, 1 closed interval, right? So this saying that I has to be greater than some negative number, just smaller than negative 1, that means that all the i's that are in the range that we care about, the 0 to 1 interval, they're all going to protest. So R equals, what do you say, Ri equals P for all I. The rationalizable strategy for player I is P, and this is true for every single player I, right? So again, we had when alpha was equal to 3, we had P being the dominant strategy for 1/3 of the population, but under the common knowledge of rationality, everyone knows this, which means even more people than that 1/3 will protest, which is common knowledge, which means even more people protest. And we get to the point after a couple rounds of iterated dominance that everyone protests. This exercise will be the same process for any alpha greater than 2. If you did alpha equals 2.2, it would take longer to unravel, right, to get all the way down to 0 protesters. If you picked alpha greater than, if you picked alpha equal to 8, you get there very fast. It would be a dominant strategy for nearly everyone to protest, and then the next round of iterated dominance, everyone would protest. Person number 0 you'll never, regardless of how big alpha is, you can always find that person number 0 does not have a dominated strategy. So person number 0, with those utility functions, because alpha doesn't matter to that person, and that if that person believes that someone will that everyone stays home, then that person will always have staying home being an option. It's never a dominating strategy, and that's also true for a positive fraction of people for any alpha. That fraction gets smaller and smaller the bigger that alpha is, but it's always going to be the case that you need 2 rounds of dominance, 1 round of rationality, and then 1 round of iterated dominance, at least, to get us down to the rationalizable set. The closer you are to alpha equals 2 from above, the more rounds it potentially takes, okay? But you're always going to get to the rationalizable outcome of everyone protesting if alpha is greater than 2. If alpha is equal to 2, it's possible that no one protests or only a subset of people protest because no one can bank on anyone protesting, right? Person number 1 is indifferent. He might protest, he might not. And person number 0.99999, even is close to 1, does not have a dominant strategy. She's very likely to protest because under almost all belief she will protest, but it's still possible she doesn't. And that's true for everyone. And that summarizes the social unrest game.